Share screen. Good. So there are 5 out of 15. Now, the thing is, this word right here is critically important. It says with replacement. That means that you get what you wanted, you get the green, but you put it right back in. So what's the probability that the next marble will also be green? Yeah, it's the same thing. Second verse, same as the first. Like when you return that green marble, you're returning the jar to its original state. And at this point, you would be wise to reduce the fractions before you multiply. So like I would reduce them both down to 1/3. And then when I multiply them together, I would get 1/9, and that gets a box.
Oh, that's right. I did it a different way.
Did you get it?
Yeah.
Nice.
I like a breakdown my call replacement.
Replacement is when you put it back. Yeah. So like you put it back in the jar. So the jar returns to its original state, basically. It has the same of everything. Now this next problem says without. So that means that when we draw the things that we want, we get them, but we set them aside. And now the jar's all out of whack. You don't put it back in. Essentially, yeah. I mean, you subtract. Sometimes you just subtract from the bottom. Sometimes you subtract from the top too. It just depends. Like, let's look at this problem. So here's what we want to happen. We're going to draw 3 marbles. So I know right away autopilot kicks in. I'm going to draw a fraction, a second fraction, and a third fraction. Each of those fractions is representative of one draw from the jar. So in its untainted state, when I pick my first marble from the jar, what is the probability that it will be, look over here, red? That's the first one that the problem says. It is 6 out of 15. And no need to reduce right now. Let's just keep talking. Now, you took a marble out and you have to assume that it was red. So now you've got one red marble sitting over here like that. You see, there he is. We got him. You always assume in probability questions to keep the problem alive that the things that you want to happen are happening in succession. So we got a red. Whoop-de-doo. Now you have to be smart and say to yourself, how did that affect the lay of the land? Well, here's what it did. First off, it dropped the overall number of marbles in the jar to what? There are only 14 marbles left in the jar. Now, the next question wants us to get a green. I circled it down there in the corner for you. How many greens are in the jar? Yeah, and because we didn't mess with that, like it says there were 5 greens, and we didn't take a green in the first step. So all 5 greens are still there. Now, the most common error that I saw is people just got on a roll and they put 4 in where the arrow's pointing, and we need to talk about that. It just was a logical assumption. You're like, oh, I remember these. This is where the numbers just keep getting smaller. You just need to be more careful. First off, how many marbles are now in the jar overall? There's 13 now. So yeah, that is true. The bottom does change to 13. However, the top is not 4. You remember, we're trying to get another red marble out. How many are there left? There are still 5, because at the beginning of the problem, I pulled a red and there were 6, but I pulled 1. He's sitting right over there with the arrows pointing to him. There he is. So there are still 5. I can't teach you that other than just to tell you that every time you do something, you are in control. You have to stop, put your pencil down, think about the lay of the land. How many of these are there? How many of these are there? Build a fraction, move on to the next one. That's it. Step by step by step by step by step. At this point, you do need to reduce the living dickens out of this thing. So I divided this one both by 3 and got 2/5. I divided, I think, maybe, was that it? You could do a little bit more. You could take this 5 and this 5, or you can also just type the whole dang thing in your calculator and it'll do it for you. But at the end of the day, it winds up being 5 out of 91. That's the reduced form of that. So reducing is kind of a personal thing, how you like to get there. Some people pick at it and some people just go brute force. Any questions on page 1? All right, then we find ourselves now on page 2. And again, feel free, please, just to ask. And you don't have to like raise your hand and wait for me to call on you. If you have a question, you just interrupt me and let me know. Let me help you. So this is our spinner that we're going to use. The first thing we need to understand is that there's 20 spaces. There's no 0 here, so what you see is what you get. What is the probability of landing on a multiple of 4? This again begs the question of, should I show my work? And the answer is yes. Like I need to know that if you put an answer down, if it's wrong, I need to know why it's wrong. If it's right, I need to know why it's right. The multiples of 4 would be a really courteous thing to list here. And the multiples of 4 are 4, 8, 12, 16, 20, 24. But I stop here because I'm out of numbers that are on the spinner. This is what showing your work means, is saying, let me make a list for you of all the winners like you've asked me for. So how many spaces are there on the spinner? How many things can happen if I flick that spinner? 20. How many of them are multiples of 4? And that is a beautiful, like no one could look at that and question, how did you get that? Then I reduce it down and my answer is 1/4. Question number 10 says, what's the probability of landing on a number less than 9? And I feel like, again, as a courtesy, I would just list the numbers that are less than 9. And they are 1, 2, 3, 4, 5, 6, 7, and 8. All those constitute less than 9. And how many is that? That's 8. And that's out of 20. And then I reduce that by dividing those both by 4. I get 2/5. This one kind of made me say some dirty words, which I won't say because well, I'll try not to anyways, but I'm recording, so especially not right now. Question 11, what's the probability of landing on a prime? Whatever would inspire you to not name the primes is beyond me, but we won't make this mistake again. Assume that the prime number problem will be on the retake or something like it. Make sure you list all the winners, okay? So let's go through the primes. The first prime number is not 1, it's 2. 1 is not a prime. Okay, to be a prime, you have to have 2 factors, and 1 only has 1. So the prime numbers on this wheel are 2, 3, 5, 7. Skip 9, though, but we do want 11, and we do want 13. Skip 15. 17 is definitely a prime, and 19 is definitely a prime. Those numbers are all prime because they have exactly 2 factors, just 1 in themselves. That's what makes you prime. How many are there on that list? Yep, and that again starts out then as 8 out of 20. Kind of feel like you're doing something wrong if you get the same answer twice in a row, but no, it just is what it is. 2/5 yet again. Different reason, same answer. These next ones, again, I say to you, gosh, what a nice thing to list the factors of 100. And this is where having something like a factor sheet might benefit you. So to list the factors of 100, here they go. There's 1, 2. There's not a lot of factors of 100. 100 is such a cool number, but he's pretty. I don't have a lot. So it's 1, 2, 4, 5, and then 6, 7, 8, 9 are out. But then there's 10, and 10 marks the center of the factor list. You've seen people make factor lists like with little rainbow connectors. 10 is the center. And so then I know I can just pair off and make rainbows. Like who goes with 5? Well, 20 does. Who goes with 4? 25. Who goes with 2? 50. And then, of course, there's 100. Now, the question is, of that list, which ones can I omit? I mean, which ones can I kill? Which ones can I get rid of? Anything over 20. So the 25, 50, and the 100, it's like, that's good to know. But really, when I make a list of the factors of 100, as it pertains to that wheel, that spinner, I only need the 1, 2, 4, 5, 10, 20, because the other ones aren't on there. We agree? Okay. So having said that, if I spin that spinner one time, the probability of me landing on a factor of 100 is exactly 6 out of 20, which will reduce to exactly 3/10. Done. Good. Mike, are you still with us? Good. Now we have to use that answer and apply it to question 13. And this is exactly the same as question 2, and it's exactly the same as question 4. Remember those where we take a probability and we apply it to like an experiment, like do this 100 times and make a prediction. Well, this one is the probability of me landing on a factor of 100 is 3/10, and I'm going to do the experiment 200 times. Third verse, same as the first. There it is again. You take the probability that you calculated and you apply it to a number of go rounds. Then again, how you get from point A to point B is between you and the fence post. But like you've shown work, you've done your due diligence. I personally do it in this order. I go 200 divided by 10 is 20. 20 times 3 is 60. Done. If you're not comfortable with that, remember you can always do 3/10 and then put the 200 over 1, and then you can multiply straight across and then reduce it later, whatever. Any questions on that chunk, the spinner chunk? I just took this fraction right here and I divided the top and the bottom both by 2. You should always reduce your fractions. Better? Okay. Anything else? Okay. Let's head down to the other spinner, and these are notoriously, almost without a doubt, the hardest ones on a quiz like this. So here we go. First off, there are 10 things on the spinner. So it wants to know the probability of landing on a space that is striped and odd. I bolded and underlined these because I'm just trying to really drive the point home of the difference between and or. How many cards do you see up here that are striped and also have odd numbers on them both? I do, and I'm going to put little marks and then I'll erase my marks as I go. But for this individual problem, I'm going to mark this one because it is striped and odd, and I'm going to mark this one because it is striped and odd. You cannot find another number on that spinner that is striped and odd. That's not a challenge, like you can't do it. So the answer to this problem is that there are 2 out of 10, which again, if I divide the top and the bottom both by 2, I'm going to get 1/5. Got it? The next question says or, and this really is going back to what I said earlier. This is where we really have to roll up our sleeves and say, okay, it's time to respect this math problem. This is not as light of work as the other ones were. So when it says or, you got to go, all right, A game coming in, here it goes. This is how I show my work. I go like, this is, if you looked at my answer key, you'd see something like exactly this. I wrote striped equals, I wrote odd equals, and then I wrote both equals. How many striped cards are there, or striped spaces on the spinner? There are 3. How many odd numbered spaces are there on this spinner? Good. Now, if it weren't for math being so confusing, you could just do 3 plus 5 and put 8 over 10 and be done. But again, this has come up so many times, but I'm just happy to keep saying it. Why can't I stop at 3 plus 5? Because I counted somebody, maybe 2, 3, 4, 1, none. I don't know. I have to say, did I count any cards twice? Were there any cards that got counted as striped and odd? There were 2 of them, and I'll even mark them for you. This one and this one got counted as striped. They also got counted as odds. Therefore, since there are 2 of them in the overlap for both, I'm going to write 2. And now the math problem to me is clear. I do 3 striped plus 5 odds minus the 2 that were in both. 3 plus 5 is 8 minus 2 is 6 out of 10. Reduce it to 3/5. Once you get it, it's not hard. I'm really glad to hear that. That's fantastic news. And anytime throughout the rest of this Mullendore, when we see the word or, that's generally going to be the practice. We add and then subtract the crossover. Yep. Because these 2 cards with the stars on them got counted twice. They got counted in the category of striped, didn't they? Oh. And they also got counted as odds. And you don't get to count. It would be like if I was going to count, I've used your example before. If I was going to count up people in my student whose names start with P or are female, I'd have to subtract 1 because you're Peyton and you're female, correct? So you got counted twice. So I would do -1 because you were in both groups. You with me? Okay. Let's head on down to problem number 16. And in problem number 16, we have an and that's great news because ands are not add and subtract. Ands, I hope you get this in your notes, theoretically should be a trillion times easier. Okay, to be shaded and even just means I'm looking for the crossover. How many cards do you see that are shaded and even? I'll mark them. I see those also. I see the 4, the 2 is a shaded even, the 4 is a shaded and even, the 6 is a shaded and even, and the 8 is a shaded and even. There's no addition and subtraction necessary. I'm just looking for the 4 that meet the 2 criteria, and that's it. Game over. So there are 4 cards that are shaded and even. I stick that out of 10, I reduce it, and I am done. Ands are like a walk in the park.
What numbers?
Smooth.
I don't know.
To put the big one on the top? Muy interesante. And now look, it's game on time, right? So here we go, Trinity and anybody else. Let's practice this bad boy. We get to do another or. So shaded or even. So here we go, shaded. This, if you're looking for a way to do these, I'm giving you the best I have right here on the board. I'm going to tell you, write down the number of each, write down the number of crossover. It's just one-stop shopping, easy. How many shaded cards are in that diagram?
4.
I'm going to write that down, 4. How many even, if you keep looking at the clock like every 2 minutes, A, I'm going to get a complex, and B, I'm going to go throw something at it so it breaks, okay? How many even cards are in the diagram? 5, very good. But at this point, remember, because it says the word or, I have to consider that there are some cards that might have been counted twice. And this is where you just put your nose in the problem and say, here I go. So shaded and even are the ones I'm looking for. And I'm pretty sure that this card, I keep calling them cards, that space, that space, that space, and that space, you would agree, got counted as shaded. But they also got counted as evens, didn't they? And how many then of them are there? There are 4. So basically for the both, I have to write 4, and then I have to do 4 plus 5, and silly as it is, minus 4. Or means to add and then subtract if there's overlap, yes. Nope, overlap means that 2 things were true at the same time. You got counted twice. Like the 2 sets like
So was I
overlapped.
counted on for not sure?
The answer to this one is 5 out of 10, which reduces to 1. I don't know.
You just said work. You circle number 5. You said that.
Yeah. If you didn't show work, like next time when we do the retake, whenever it is, like later this week, if you don't show work, I'm just like, even if your answer is right, I'm just going to blanket say, like, but if you didn't figure it out, by the way, you probably haven't done the math yet. Each problem was about worth 2 points. So like 1 point for an answer and 1 point for a good justification, right? So expect that. It's not perfect math, but that's about 2 points per problem. So show your work on everything. Okay. Question 18 is the last of this batch, and it says, what's the probability of landing on a space that is a multiple of 2 or a multiple of 3? This is a nightmare of a problem until you understand, as Trinity now does, the magic and beauty of doing the OR problems. And here it goes. I'm going to go through the spinner, and I'm going to count multiples of 2. And multiples of 2, so let's see, multiples of 2 are, here we go, 2, 4, 6, 8, 10. That's it. Those are multiples of something. When you count by 2s, you're doing multiples of 2. The multiples of 3 are same thing, just count by 3s. 3, 6, 9. And of course, you could keep going, but they're not going to be on the spinner. So now the question is, if I just look at these as what they are, how many multiples of 2 are there? How many are on this list? There are 5. So I would say, okay, there's 5. How many multiples of 3 are there on this list? So right now, at this point, I feel like I could just do 5 plus 3. But again, and 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 again, when it says or, I've got to look for the ones that got counted twice. Do you see any numbers that got counted as a multiple of 2 and also as a multiple of 3? I agree. This number right here, I'm going to put a purple box around it. He got counted twice. He says, you can count me as a multiple of 2, or you can count me as a multiple, but please don't count me twice. So there's one of him, right? So I do 5 plus 3 minus 1. Because there was exactly one item in the overlap, in the crossover, in the look at me, I'm in both groups category. What's 5 plus 3? What's 8 minus 1? So the answer to this one is not reducible. It's just 7 out of 10. Next page, page 3. We're looking on this one to get, by the way, as soon as it says 4 dice, I'm sorry that I'm so predictable, but this is what I do, and it's what you should do. I go blank fraction, blank fraction, blank fraction. Like if you didn't get that memo, that's really what we should be thinking. That each of those fractions represents a probability that I have yet to determine. So here it is. What's the probability if I roll a die, just a standard 6-sided die, that it will show a factor of 12? What's something my teacher might want to know at this point? What are the factors of 12? Like, I sure wish someone would tell me what they were. So here I go. I know my factors. They are 1, 2, 3, 4, 6, and 12. But I'm not going to list 12 because he's not on a die. So there they are. How many of the 6 things that can happen when I roll a die are called factor of 12? 5. And if I want to do this exact same activity, roll a die, roll a die, roll a die, roll a die, does the probability ever change from one to the next? No. Again, like I've said before, dice don't care what the other dice do. This isn't like, well, this die looks at this homie and says, well, he got a factor of 12. I better come up as a 5. They don't care. Every die is exactly 5 out of 6. And so you write it down. 5 out of 6 times 5 out of 6 times 5 out of 6 times 5 out of 6. That's it. And then, of course, you have to multiply this out. So this comes out to, by the way, here's a pro tip, a life hack for those of you that are listening. Aiden, you should hear this one. Oh, he's out like a light. Screw it. Micah, you're still up, right? You sure? Pro tip, life hack. I find this, I wish someone, actually, that's a lie. Someone probably told me this. I just probably didn't remember. I wasn't listening. Might have been sleeping. If you ever have a chain of multiplication like this, and the fraction itself cannot be reduced, if you multiply a bunch of copies of that fraction together, the answer cannot be reduced either. And I'm telling you that because I think it's rad. Think about this. Like when you multiply 5 times 5 times 5 times 5, you get 625. Ooh. And then you do 6 times 6 times 6 times 6, you get 1,296. And then a normal person would look at that and say, I wonder if I can reduce that. But if you heard what I just said, since you got it by making a bunch of multiplies of an unreducible fraction, take it to the bank. He won't be reducible either. That's a life hack. I did 5 times 5, which is 25. And then I did 25 times 5, which is 125. And then I multiplied by another 5, which is 625. You just multiplied all the tops together, and I multiplied all the bottoms together.
Like 25, you know what I mean?
I do, but in a case like this, you just wham them all together, multiply them, done. That's it. Final answer on that problem. Good. Question number 20. If you're going to flip 8 coins, again, if you are at all confused as to how to do this, here is my standby explanation. Put a fraction for each one of the 8 coins. And of course, we can use exponents. Well, that's 7, so I need another one. All I want to know is this. What's the probability when I flip a coin, flip, that it lands on tails? Quick, what is it? Okay, how about the second coin? Right. So listen, if you want to write it all out this way, you are more than welcome to. But, you know, someone created the notation of exponents for a reason. Rather than multiply something by itself 8 times, how about we just use this notation? 1/2 to the power of 8. And what it comes out to be is, of course, 1 to the 8th on top is 1, and 2 to the 8th is like 250, 256. So that means that if Haley sat down with 8 coins, and she went flip, 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 for them all to land on tails should only happen 1 out of every 256 tries at that experiment. That's theoretical. Could it happen on the first try? Yep. Could it take 1,000 tries? Yep. Theoretic probability is what should happen in a perfect world. Number 21, if you roll a die 3 times, so you know what I'm going to do. If you haven't gotten this memo, I just wonder if you're listening at all. Rolling a die 3 times, fraction times fraction times fraction. There it is. Now, I want to know the following things. What's the probability of my die landing on an odd number? 3 out of 6. Yep, good job. What's the probability of my die landing on an even number? 3 out of 6. And what's the probability of my die landing on an odd number, the third one? Oh, remember, dice don't care what the other dice do. The third die isn't like, well, I can't land on this because my homie over there. Dice don't have emotions and they don't physically affect each other, right? 3 out of 6, 3 out of 6, 3 out of 6, which also, of course, reduces to 1/2 times 1/2 times 1/2. At the end of the day, it becomes 1 out of 8. Done. End of story. This next question isn't so much a setup problem. There was one person, Aubrey's method for doing this problem made me just stop what I was doing and marvel. So beautiful what she did. For the rest of us, the most common approach to this problem is this. First off, if I roll 2 dice, how many things can happen? Nope. Nope. There are 36 things that can happen if you roll 2 dice. And I'll tell you why. If I roll a die, 1 die, how many things can happen? 6. If I roll another die, how many things can happen? And 6 times 6 is good. So let's get that out of the way first. If Evie grabs 2 dice and rolls them, there are 36 different outcomes, like 1-5, 5-3, 6-1, 2-5, 3-1, 3-4. There are 36 such combinations like that she could make. Now, the question becomes how many of them have a sum of 7? This is not a time to do real math. This is a time to just roll up your sleeves and go. Here we go. One possibility is that the first die could be a 1 and the second die could be a 6, right? And this is a very intelligent approach because honestly, it takes like 20 seconds. The first die could be a 2, second die could be a 5. They could both be 3s. The first die could be a 4 and the second die could be a 3. Did I put 3 and 3? I meant 3 and 4. That's my bad. I apologize for that. And then there's a 4 and a 3. And then, of course, the first die could be a 5. Second die could be a 2. First die could be a 6. Second die could be a 1. Like, would that take 20 seconds? And that was with a screw up. How many of those outcomes are there? 6 out of 36 is the answer, but now you have to reduce it, and it becomes 1/6. And that marks the end of the first day. So, do you have any questions to this point? All right, let us press on to day 2. And these are all stapled together, so you can just head on to your next page. Problem 1 can be done pretty shortcutty. The way I personally did this, if you were to look at my answer key, is I just wrote 10 factorial. Listen, if you ever want to arrange people, the logic behind this, and I'll show it to you here in a second, is the answer, by the way, is really big. It's like in the millions. It's 3,628,800. Now, the logic behind this, if someone was sitting there going, why? Like, why does that work? I can explain this, and I guarantee it has to make sense. Here are the 10 seats of the people being arranged for a photograph. Picture 10 chairs against a wall, 10 people sitting down, and then someone says, okay, I'm going to start placing you. How many people could go on the far left? You have 10 to choose from, right? Now, once someone's sitting there, how many people can sit next to her? There's only 9 left to choose from. Once you have 2 people seated, who can go next to Sally and Rick? How many? 8. As the pool dwindles, every time I place someone in a seat, my pool is dwindling by 1. I don't give a rat's fat kahooshka like who I'm putting in. The point is when I place somebody, they're not in the pool anymore. So it goes from 10, 9, 8, and it goes all the way down 7, 6, 5, 4, until you're the last person who's like, well, I guess I'm the last person. I guess I'll sit on the right, and there's only 1 to choose from. That's why 10 factorial is it. Simple, pimple. Any questions on that? Question 2, we are electing a president, a vice president, a secretary, and a treasurer. That's 4 seats being elected out of a group of 15. And does order matter when we elect presidents and people like that? Of course it does, right? You can't just pick those 4 people and say, oh, it doesn't matter what order, like who's president and who's treasurer makes a big difference. So this is 15P4. Unless you don't like that explanation, I can do exactly the same explanation as I did with the chairs. And I can go like this. Here's a seat for the president. Here's a seat for the vice president. Here's the secretary, and here's the treasurer. If the 15 people have run their names into the ballot, how many people are eligible to win president? 15. But once someone is elected president, how many are eligible for vice president? And how many are eligible for secretary? And how many are eligible for treasurer? And at this point, we stop. This is not a factorial. You stop because you're only electing 4 seats, not all 15. Both of these, type them both into your calculator. They will give you the same answer. And that answer is 32,760. Do you have any questions so far? Okay. Question number 3. If you did miss this, I would just ask nicely that you please never do this again, okay? This just is going to be here. This is a fundamental counting principle problem. You take the number of pants, the number of shirts, and the number of shoes, and you just simply multiply them together. 6 times 11 times 4 is 264. This is assuming that Sven picks 1 pair of pants, 1 pair or 1 shirt, and 1 pair of shoes. Like if he just selects 1 from each category blindly, there's 264 combo outfits that he could make. Any questions there? That's just the fundamental counting principle. Nothing to it. There's almost no meat on that bone. Let's head on to number 4. The only way I can really show you how to do this problem, other than just showing you the way that would take literally like an hour, because we did this once where we actually tried to list out all the combinations, and you might remember it took some doing. Like it was way back weeks ago when we first started this. It was a pain. So we have a formula for this, thank goodness, and it looks like this. There are 20 people, and I'm going to do combinations of 5. Why do I know to do the C and not the P? Why C and not P?
I said NCRs, that's still correct?
Yeah, NCR is what your calculator says. Why NCR and not NPR? Why C and not P? And why do I know it's a combination and not a permutation? It's good job, Haley, because order doesn't matter. With a committee of people, the order is irrelevant. If you just grab a group of 5 people, they are what they are. It's a group of 5. We don't care. So when order doesn't matter, we use the C. So this is 20C5, and that one comes out to be 15,504. End of story. Okay. The same thing can be said of problem 5. And I know that you're welcome to disagree, but what happens here is with a hand of poker or a hand of cards, the order that I get them in doesn't matter because I'm going to rearrange them myself. So this is another C problem. There are 52 cards. I'm doing combinations of them 4 at a time. Do not do P on this because order doesn't matter. Same 4 cards are the same 4 cards. I'll put them how I want. 52 C4 comes out to a lot. There are 270,000. I'll see you tomorrow. Okay. So there are that many combinations in a four card combinations of a deck of cards. Question number 6 is, I mean, it straight up says combinations, but oddly enough, a locker combination is kind of an ordering problem. So that's what a weird quandary. The simplest way to explain this to you, as I always have, is to put your 4 blanks. The best way in the world to do a combo problem like this, a locker problem, is to put the blanks. So this is a 4-number combination. It's not very standard to have a 4-turn dial, but I imagine it exists. And as we discussed in class, I hope you didn't fall for this, but the numbers from 0 to 75 contain 76 numbers. I hope you remember that conversation, that if you start with 0, you have to add 1. So like if you count from 0 to 10, you actually say 11 numbers, not 10. So there are 76 numbers on this dial. The numbers in the combination must all be different, which means I can't repeat, which means they'll descend. My first number can be 76 different things, but the second number says I can't be the same as you, so I'll be 75 options, then 74 options, and then 73 options. And if you multiply those together, you get 30,791,400 different combinations if you had a 4-turn dial with the number 0 to 7. You good? Okay. Question 7 says, in how many ways can a 6-question survey be answered if each question can be answered with one of the following? It really isn't that bad. I just count them and I go, there are 1, 2, 3, 4, 5 things that can happen. And how many times do I have to answer that question? 6. So if you want to show it old school, question 1 can be answered 5 ways. Question 2 can be answered 5 ways. Question 3 can be answered 5 ways. Questions 4, 5, and 6 can all be answered 5 ways. And if you type that into your calculator, you'll get 15,625. But again, why do we use exponents in math? Because it saves time. When you're first learning exponents in algebra, it's annoying to learn all the rules. I get that. But at the end of the day, they were just meant to save time. It's just a notation to save time. So rather than write out 5 times 5 times 5, la, 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 you could have, of course, written just 5 to the 6th power like that. Because you're answering a 6-question survey. So you repeat that activity 6 times. That's why. All right, let's see how much of this. I think we can get quite a bit more done. We might be able to finish. We might not. Let's give it a go. Question number 8 says you're going to roll a die 5 times. And how many different ways? So this, you know what I'm going to do. I'm going to hop in and write my 5 blanks. I would be really creeped out if you still did not get the memo that that's what we do. Just FYI. So there you go. There's our 5 dice, or the 1 die being rolled 5 times, however you want to say that. And I'm going to put multiplication signs in between them. And I'm ready to go. Here it goes. So I got to go through and count them up. Here we go. First roll is even. How many ways are there to get an even on a die? Done. 1 down, 4 to go. How many ways are there to get an odd? How many ways are there to get a prime? Yes. And the primes are 2, 3, and 5. How many ways are there to get a 3? And how many ways are there to get a factor of 5? 2. The factors of 5 are 1 and 5. And there are 2 of those. Just a grind, man. Just go 1 at a time. 1 at a time. You multiply that all together, you get 54. So if I rolled a die 5 times, there are 54 ways. 54 uniquely different ways that I could get even, odd, prime, 3, factor 5. Not that anyone's interested, but still good to know. Question 9, does order matter?
No.
Yes, it does. Like the order that you take your classes in affects your schedule. So this is a P problem. So I have 14 and I will do permutations of them 8 at a time. And your calculator will do this, Evie. If you don't know how, I'll just show you. Okay.
Oh.
Any scientific calculator will do the permutations and the combinations.
Oh, I did it since in class. That was my thinking.
Oh.
Yeah.
So you can't, this formula accounts for that, but you can't take the same class twice.
But you said it matters like the way the schedule's laid out. And I was like, oh, my thinking was never mind. Yeah.
First period, you can take 14 classes. Second class, you have 13 to choose from. So what did I do? Oh, that's my bad. I was doing a lot of things at that time. Did you put 14 P8 on your paper? No, that's my bad. I apologize if I wrote the wrong thing. I write about 724,000 things a day, and every once in a while, but I'm really sorry that I wrote the wrong number. It should definitely be 14 P8. That is my bad. I'm sorry for the confusion. We ready for number 10? How many different 4-digit integers are possible? Gosh, I wonder what I should do. Oh, here's an idea. Let's do 4 blanks like we always do. And I just need to think about, okay, here's my pool over here of numbers. I can pick from them, but who can't I pick to start a 4-digit integer? Yeah. I can't. So I need to go through and count and say there's 1, 2, 3, 4, 5, 6. There's 7, but one of them is a 0, so I only have 6 that I can choose from. From here on out, honestly, it's a dang free for all. It could be 0, 0, 0. Like there's no more rules other than the first one can't be 0. So from this point on, it's just 6 times all of them, all of them, all of them. 6 times 7 times 7 times 7, which is 2058. And we are going to finish, so this is good news. We didn't make it by much, but we got a ton of time in my world. So let's get to the last 3. When it comes to this two-way table, what is the probability that a randomly selected contestant was from the US and scored up to 100 points? Remember, the word and is massively powerful. It says you have to be both things. So when I look at this table, the first thing I want to do is count the total. So off to the side, I wrote total equals 67. Sometimes it's a good idea to count that twice and just make sure that you got it right, because that's going to mess everything up if you don't. All right, so here it is. I look in my table for the people that are Americans or from the United States and scored up to 100. Up to 100 and American looks like exactly those people right there. If you're in that little thing I circled in red, you scored the correct number of points and are from the United States. So I just go, there's 13 of you out of 67. Done. Type it in your calculator. That one came out to around 19.40%. Whoever you are, you must put zeros. I don't remember who you are. It might be Diedrich, it might be Aubrey, it might be Dalton. I don't know. But if you're here in this room and you got dinged, putting 19.4, I get that it feels like it's right. But when someone says round to the nearest hundredth, zeros stay. Okay. The nearest hundredth means I need to see the hundredths place, even if it's a zero. Okay, good. Number 12 says, what's the probability that a randomly selected contestant was from Canada? Or you got an or. You know what that means? I gotta go and I gotta say, okay, Canada is these people, and that's a total of 33. Scored over 100 is these people in the other purple oval, and that's 21 plus 15 is 36. So for over 100, I'm going to put 36. But Trinity and anybody else, what have I failed to consider up to this point? I counted these 15 people twice. They're like, make up your mind. You can't count me as a Canadian and then also count me as a, pick one category to put me in. So since those 15 people got counted twice, I'm going to put both equals 15. And then the math is 33 plus 36 minus 15, which done correctly comes out to 54 out of 67, which rounded correctly comes out to 80.60%. And the final problem, and then we'll get out of here, is a given problem. So it says, given that they scored over 100, in fact, let's resume. We almost made it. I don't want to make you late. There's 1 minute of class. I'll cut this off. Remind me tomorrow. Don't throw those away. Obviously, keep them. We'll get them back out tomorrow, and we'll go over anything else. I'm planning retake for Wednesday. I might bump it back to Thursday, depending on a couple of different things. Got it?
Thursday, I will